So hello everyone, this is Christian Gagné. Today we have David Beauchemin who will present detection of duplicates among non-structured data from different data sources. This is, if I understand well, basically the topic of David's master's thesis. So David, please go on. Thank you. Hello everyone, can you hear me?
Yes.
Okay, did you understand? Did you heard what the announcement I made of David?
Yes.
Okay, sorry. I mean, I think that David.
Yeah, I didn't. I think he was not like listening. That's why.
Okay, but he said, il m'a dit je suis prêt. David, on t'attend.
Okay.
I'm here, sorry. Bad configuration of my computer. Do you hear me?
Yes.
Yes.
Okay, perfect. Sorry for that. Thank you, Christian, for the presentation. So I will start by presenting today the detection of duplicate among unstructured data from different data sources. This presentation is about my master thesis, and I will first start by explaining the title, and after I will go around to the presentation. So the first part of the title is detection of duplicate. What I would mean by duplicate is, and detection of duplicate is to find one or more representation of the same thing. So let's say I want to find in a database my name if it occurs, and I will try to find the duplicate of that. Non-structured data means mostly data that's not structured in a column type. So let's say like text, you have a lot of information in text, but they are not structured. You need to extract the information in the text to be structured. And different data source will means having yes, sorry Pierre, I will try to be to speak closer to my computer. And for data source, I will mean using more than one data source. So yes, okay, the situation. When assessing a commercial risk, an insurer needs to gather various information about a risk. So let's say his name, his address, and other information. This long and complex process implies numerous questions that you need to ask to the person trying to be insured. Thus, an insurer is prompt to use an external source to help produce a number of questions. So let's say I give in my name to an insurance. Maybe you want to extract information about myself on my Facebook or something like that. Or for commercial risk, maybe let's say I want to extract if from my website any information about my companies, and thus reducing the number of questions that I need to ask to myself to gather the information in order to define a premium for their insurance product. Thus, we want to detect duplicate of commercial risk in another data source using as little as possible information. What that means is I want to use, let's say, the name or the address only, and I'm trying to use less and less information to gather the more information possible. I have an example. So let's say David Beauchemin myself, I'm an owner of a company which called Beauchemin Inc., and I call for insurance. Using minimal information, the insurer wants to retrieve as much information as possible from external source that can be any type to ask myself the less question as possible during the questionnaire for determine the premiums. But now, how do we detect duplicates? In our case, we will work only with two databases. So we have a database one and a second one. and when use a duplicate detection model and retrieve as much as possible duplicate of, let's say here, Laval University. So from the database 1, we want to retrieve the duplicate in database 2 of Laval University. But in our case, we are interested only in the top one document as the potential candidate. So we will keep in mind the other one, but we will only retrieve the first one as the solution, as the response of our duplicate detection model. So in our case, to detect duplicate, we need the following two: a database, which will be explained in section 2, and a way to determine the similarity between two documents. We'll discuss in section 3. Firstly, the database. We have two options. The first one is the Registre des entreprises du Québec, which consists of about 3.5 million entries, containing the name, the address, economic activities, administrative information about roughly every entries that have been made in the Registre des entreprises du Québec. So it's not 3.5 million entries, unique entries. They can be multiple occurrence of the same one. So let's say I created an enterprise, but I forgot to update information. They will remove, they will radiate the enterprise, and I need to create a new one with the same name, so they can have multiple entries, and it's normal in this context. So it's not unique entries, but it's 3.5 entries in the database. Why do we choose this one? Was mostly based on the availability of the data. There are other enterprise data sets out here, like let's say Yelp data set, but our primary research shown that those data sets don't have a great overlap of every type of enterprise. Yelps mostly rely on business that give service to clients. So in our case, there was not only that type of enterprise. So the regist was a good way of exporting a full data set and have a good overlap with the private one. Speaking of private data set, in our case, we have a data set consisting of 21,444 enterprise, and we have for them the name, the address, and economic activity. We have one name, one address, and one economic activity for each. Merging the two private data sets, we focus since we have the Registre des entreprises du Québec, we will focus only on the one who have an address of in the province of Quebec. So with filtering the addresses with only residency in province of Quebec, we have 11,649 commercial risk. From them, I annotated 1,706 one, creating two type of pair. We have the first one, which will be known as the positive example. I have 1,418 example of that, composing of the commercial risk and IRQ entity. By that, I mean that manually, I've been searching the name of the enterprise to get the representation in the Registre des entreprises du Québec, and using the unique number, the IRQ number, I match it with the commercial risk. So in that pair, I will have, like, let's say Beauchemin Inc. and an entity number mapping to the IRQ. The other one being a negative example, and 288 of them, will be an example where trying to find that risk in the IRQ was not possible. So I was searching for the name. After that, trying to Google search to find if the name was correctly written or any form of the name that could have changed using the address and everything. And that was not possible to, at that point, map to an IRQ entity. That means that it's possible that it exists under another name. And in some cases, I don't have the legal obligation to register my enterprise. In some cases, like let's say I'm a, sorry, I don't know the word in French, but travailleur autonome. I don't need to register my name in the Registre d'entreprise du Québec. So in some cases was that, other case it was maybe possible that the name was not correctly written, or it was registered somewhere else. Like let's say from if it was Canada World War Canada or a Canada-based enterprise. So, like I said before, we are trying to work with as minimal information as possible. So we will only use the name and or the addresses in our cases to try to find as much information as possible. But as we can see in the list, there's another a possible field comparison will be economic activity, but we will not use it, and I will discuss a little bit later something about it. So now, we have two type of information, but they are not normalized, so we construct two variant of the name. So starting from the raw name, we will have the first name called what we will be called the normalized name, which consists of lowercasing the name and applying a white space trimming from the at the end and the start of the sentence of the names, and removing all the accent in the name. The reason for that is mostly because they are French and English names, so it is a little bit easier to map some name between them. And the second name would be the removal of the stop word. Uh, what a stop word is a word that don't give a lot of meaning in the name. So let's say le, la, de in French. So we applied the French one and the English one, stop name removal on on every name. So we have an example here. So if we have the Université Laval, the first normalized name would be Université Laval in lowercase and without accent. Uh, and if we remove the stop word, we will mostly only remove the first le of Université Laval. And now for the addresses, there's two address variant of the address. The first one being mostly the complete address normalized, just raw, but applying the same previously on the name normalized pattern. So trimming of the accent, removing of the white space, and lowercasing the address. And the second one is the address component. And this part is based on intuition that writing address is there's no standard is writing address. So I can write the civic number followed by the unit number, or unit number followed by the civic number. So we wanted to compare if without without using the full structure, but mainly comparing only the group of the component of the address. So let's say comparing a two civic number of two address and match if and verifying if they are similar, and doing the same thing for the rest of the components, we could maybe have a better similarity of the address. So for that, we developed a parser that was presented 2 weeks ago from with myself and Yassine, Aaron Yassine, that mainly tag every address, every component of the address, and further on we group them by components. So I have an example here. The postal code was grouped, was tagged G1V was first element of the postal code, and OA6 was the second one, and we grouped them to form the postal code. And later on to compute the similarity, we will compute the similarity of every component using the same matrix, and we'll do average mean on all of the component to give the final similarity of two address component comparing to. So now the similarity between two entries. So that is the second part of the work. So we need to find a way to compute a symmetry between two entities. We will mostly we have mostly worked with two approach: similarity algorithm and machine learning approach. There's other possible solution, but Since we mostly rely on at most two attributes, it was difficult to use probabilistic approach or other approach because they mostly rely on more than two fields. So we put them aside and we work it mostly on those two. So for the first one, the similarity algorithm mostly knows at it is a well-known approach in NLP, natural language processing. So it consists of using a similarity algorithm that takes two strings and can generate a number between 0 and 1, mostly 0 and 1. Uh, and that similarity can be used after on to rank the document and choose the best one as a duplicate candidate. So in that example, there's a lot of similarity algorithm possible. We uh, we uh, we studied tens and we selected a little bit less than 10, but I will show some of them and we'll be later on discuss. So our similarity algorithm, as I said, is one that measures the resemblance between two strings based on the distance between their tokens. A tokens can be a full word or a character word. Most of the work was based on the character level, on the word level, because the character level did not show to improve the result. So I will show three similarity algorithms just to give an insight of what it is and how it's working, but it's not the core of the presentation here. So some of them will not be shown here. So let's start with the simplest one, the Jacob similarity and the most well-known. So here we have an equation, and that said is uh, if the one of the ensemble is empty, so let's say an empty string, the similarity will be 0. Otherwise, we use the number of token of the length, so the number of token similar between the two strings. So if we go an example here, in our case, if we want to compare Laval University and Montreal University, they only have one similar token between the two, so it will be resulting in one university. And the ratio is the full number of token present in the two strings. So in our case, we have Laval University and Montreal. So the similarity between the two should be 1/3. And the second one, maybe the easiest to understand, is the string to string. The string to string consists of comparing every token, either character or words, and if they match exactly at the position and the same character, it will be resulting in a similarity of 1, and otherwise it will be resulting in a similarity of 0. So if we have the example here, the string to string similarity between Laval University and Montreal University is 0, and between Laval University and Laval University is 1. So it's really a binary similarity function. And the reason that we chose this one is since we work with a pretty normalized data set, which is the Registre d'entreprise du Québec, we thought firstly that the name should be present in both places and should be present in almost the same way, written almost in the same way. It is normalized, and we will see later on if the intuition was good. And now, the last one is the Charot-Winkler similarity, which is based on the Charot similarity that, as I said before, is not the take home is not how the Charot is computed, but is mostly that is the Charot-Winklers give a little bit more similarity when two strings share a same prefix. That will be here. So it is the minimum. So usually the maximum it's used is 4. So if the fourth up to the fourth character are similar, the symmetry going to be greater? The intuition being that the symmetry between names, mostly names, starting with the similar letters, should be closer than the one with different names. So the intuition is the symmetry between David and let's say Simon should be lesser. Sorry, the symmetry between David and Daniel should be greater than David with Simon, even if they share some letters, the high. But the starting of David and Daniel is more close, so the symmetry should be greater. Here we have an example of the compute of that. So the Jarreau-Winkler is equal to the Jarreau plus a ratio multiplied by the inverse of the similarity. So it will be computed, the Jarreau was computed at 0.5. So you have a ratio of two similar letters, D and A, between the two strings. So it will be resulting in a similarity of 0.84 compared to 0.7 using the Jarreau only. Now, why do we choose to study similarity algorithms? Because they are easy to use, they need no training, and they're still give good results even if they are pretty simple. In case when we have normalized data and we work with short sentences. So now, speaking of result, we first started by working with only the positive example. So I'll be showing only the interesting result here using only the positive examples. The reason being that we use that approach to select from the 10 which one are interesting in our case, and later on we'll use the positive and negative example to select the decision function that I will speak later on. So now we see here that string to string give surprisingly good results considering that is restrictive. So using only a simply normalized name, we can match up to near 42% of the enterprise. And we also see that if we remove the stop word, we can get that number up to 44, and it gives the best results all across the board. And for the other symmetry measure too. That being shown that in some cases, people are given names that are 1, 2, or 3 stop words close to the representation either at the RQ or in the private dataset. So for an example, I could call an insurer and say that my enterprise is Beauchemin Inc., but in the Registre d'entreprise du Québec is registered as Les Entreprises or Les Beauchemin Inc. or something like that. So removing that stop word increases in most cases to 1 or 2 or 3%, between 1 and 3%. And that show that the data is pretty much normalized in the case of names. And the best results here in bold was obtained by the Jacquard at near 67%, which it's kind of good for a really simple approach using only an overlap of the number of identical word between the number of words present in the two names. At 67%, it's pretty good. It's a pretty good baseline considering the simplicity of the approach. And we show here that the prefix similarity between Jarreau-Winkler and Jarreau help to improve the results since we can reach using only the normalized name, not that much, but using the name without stop word, we can reach about a 1% increase using the prefix. That means that in most cases, not in most cases, but in some cases, the name, the symmetry, the local symmetry between the names can be defined by the starting point of the name. So that means that using the name of an enterprise it's in some case is defined by the starting point of it. So Beauchemin entreprise, it can be easier to find than using enterprise Beauchemin. That's the point of that similarity. That's what's shown in the similarity here. And sorry, and we can see here. Finally, we can see here overall that using the name can give good results near in between 44 and 66.5%. So it's a good baseline starting point, only using the name. And if we want to go now to the address, the second field attribute that we have, we can see here that first of all, the string to string did not achieve a good result. Only using the name, no match was possible. This is mostly due to, as I said before, the normalized address is not, there's no standard of writing. So let's say you want to write the province, we could write QC or Quebec like here. And that we don't have, we could define a way to transform Granada to, but the order too is not standard. So as I said before, we can put the unit number before the civic number or after, and that impacts the result of the string to string because it is not possible for that approach to match to. But if we remove that that pattern, the order, and we can achieve a 13% match. So that means that addresses are mapped perfectly if we remove the order of the components for around 13% of the address. But if we take a look at the best result with the CSS, we see that it is at 52, it is near 40% below the previous best result with Jacquard. And we also see here that the difference that we saw before with Jarreau and Jarreau-Wickler did not show to improve. So that means, and is logical, that the address is not defined by its prefix, since the prefix here is the civic number. So a civic number can be used multiple times depending on the street name. So for that reason, we did not use the Jarreau-Wickler in that case, and is logical. About the porous result, we see here, before we saw that the results are kind of below of around 40% in the best case. And that is due to the policy of the IRQ. There's 16% of the pair commercial risk and IRQ entity that are missing an address. So it is not possible to match 16% of our commercial risk. And we see, as an example here, we see that the accuracy without those pairs, so with removing that example, can increase up to 62.74%. So it's near 10% higher, but it's still a little bit lower than when using the name. And as I say, that those missing addresses are due to the confidentiality policy of the IRQ, and we cannot do anything about that because it's mostly due to the presence of an address that rely to personal addresses. So if we summarize what I've just shown to you, using either name or address, the similarity algorithms allow us to find the matched entity around 50% of the time and up to 67%, near 67% with Jacquard using the name. Using the name without stop word or the address component help improve the result over the normalized name or address. And the without surprise missing address pull down the results. Like I said before, in the results shown here, we only use the positive example. So the idea is when someone call for an insurance, we assume that the enterprise is present in the Registre d'entreprise du Québec, but in some cases it might not. As negative example I've shown, is in some cases it's not possible to find the entity. So we need to use that decision function. Here we choose to use a similarity threshold, where similarity below the threshold is rejected. So let's say we have like a comparison between Beauchemin Inc. and another enterprise, and the similarity is 0.2, and the threshold is at 0.7. So the similarity will be rejected, and this comparison will not be held as a possible duplicate. I did not show the result here because there was too many, and I will not have enough time to present all the results. But the idea is just that we use the positive and negative example to verify which similarity threshold value is the best for every similarity algorithm to maximize the result and see all they work with a negative example. Now, the machine learning similarity algorithm. We saw that using the name or the address give good result. Now, what if we use both of them? We cannot work with two-string compared to two-string with the previously shown algorithm. We could maybe concatenate the two of them, but that would not show us interesting result. So we choose to use a machine learning model. So if we have all the information to the left about one entity, and you want to compare with another one here, we will need to use a name address information vector generator to generate a vector of the comparison between the two, and use a machine learning model to, from that comparison, define a similarity value. What is that name address information vector? So the previously shown similarity algorithm can be used as information or attribute. So we have built a generator that generates an information vector between two entities using the name without stop word or the component address. It's composed of the selected similarity algorithm. So we have the string to string, Liebenstein, Jarrow-Winkler, longest common substring, and the Jacob cosinus for the name, the first row being for the name, and the second one being the addresses. So we have almost the same. So instead of the Jarrow-Winkler, we only use the Jarrow, and we also use this is the overlap coefficient. So that vector will be used to train a model and use that model to predict the similarity between the two entities. Speaking of that machine learning algorithm, we choose to use three: the logistic regression, the random forest, and a multi-layer processor. Other were explored, but the poorest result that they give, we choose not to present the result in the thesis. Why have we choose to use machine learning algorithms? Because they allow us to use the name and the address simultaneously easily, and they have a good generalization capability. Now, the model's training steps is consisting of 4 steps. The first one being the data preprocessing, the second one being an upper parameters grid search, a model training, and finally an evaluation of the trained model for the duplicate detection task. The first step, the data pre-processing. So we split the data as a matter 80-20. So the 1,706 annotated example was split 80-20. From the trained data set, the 80%, we randomly match the negative pair because we have example since we need a vector comparing one example from another one, we need to remove the none to have a comparison. So we randomly match the negative pair. So with a commercial risk and a none with a random RQ entity picked randomly. And since we have an unbalanced data set consisting of 1,364 positive example and 241 negative one, we use a double randomly generation of an example. So it consists of randomly select the first name and address of a Registre d'entreprise Québec entity to create a fake commercial risk. And later on, we use that fake commercial risk to pick another randomly pair to be matched with. So we will be obtaining a commercial risk and an RQ entity with that process. So resulting in a training dataset of 2,246 pair. And finally, we fit a standard scalar on the training datasets that we use to be applied, that we apply to transform all the data, the train and test dataset. Finally, secondly, we conduct an hyperparameter grid search in a model training. Grid search, we use a grid search for the logistic regression over the C and the tolerance of the improvement, and a random forest, for the random forest, we conduct a grid search on the number of estimators. For the multi-layer perception, since there was too much number of combination, we picked a random search of 1,000 example consisting of search over the number of layers, the number of neurons, and the tolerance to the improvement. All that was conducted using a cross-validation approach using a fivefold. And after the grid search, we train using the best parameters to obtain the trained model. Now, the evaluation step, the final one is we evaluate our trained model against the best configuration, which is Jacquard using the name, but re-evaluated with the validation data set, so the 20% of the 1,706 annotated example. We evaluate the algorithm with positive and negative example for recall and precision. The decision function is just, as said before, is a similarity threshold, where symmetry between a numerical threshold, like let's say 0.7, is below 0.7 is rejected. Our objective is to maximize the recall since we want to detect the more duplicate as possible, and we can later on validate duplication manually if there's an error, a possible error or not. Speaking of results, we first see in that table that the pole value are the best one. We see that the random forest and the multi-layer perception achieve better recall and better recall than the Jacquard at near 1% for the random forest and near 7% for the multi-layer perception. We also see that the multi-layer perception obtain better accuracy with almost 11% improvement. About the logistic regression, it is the model that achieved the lowest result, even if the Jacquard symmetry is used in the derivation of the information. We see that the recall is near 6% below, accuracy is 2% higher, and the precision is better. But since we aim to maximize the recall, that model gives a poorest result. About those error of the logistic regression is an example. So if you want to compare those two entities, we have the first one, Construction Alain Cloutier Inc. and Construction Steve Arbor Inc. With the following address that clearly for human, the address is not similar. For the name, maybe some part are identical like Construction and Inc., but for the rest, it's clear that it's not the same entity. But The logistic regression give a similarity of 0.9934 between those two, even if the annotated duplicate appear with the same name and a slightly different address. The slightly different means the street name and civic number is different. No, only the street name is different with the typo in it. But the similarity is kind of high at 0.998. That's highlight that a problem of our approach is so far we are trying to match with the most similar, and the generated similarity are close to each other, making it restrictive to use only the best similarity. So since our approach aims to pre-fill the information of an insurance application, we can return more than one result and use a human validation step to select the best one from n possibilities. There's other way to improve the result here, but I choose not to explain what other approach that we tried before, since I will not have enough time to present every result of that. But like I said before, we try to use the activity, but that was not shown to improve the result. We try to use other models. We try to improve the dataset 3 times. So we improved the dataset 3 times. And we tried to generate new feature, but it was difficult to generate new feature information without repeating the same information over and over. So I've created more noise than anything else, and we try to use a PCA to condense information that's have not shown to improve the result. So we'll continue with using an n most similar. So we consider matching is good when the pair commercial risk or quantity is included in the n most similar. Oops, sorry, too fast. Let's say we use an n of 5. If the correct pair is present in the 5, that we will consider a good the matching is good. But if it is not, we will use the first response as type of error for the compute of the precision, accuracy, and else. Now, speaking of result, we use 3 different n value. The first one being 1, all the previous results. The second one being 5, enter. I was explaining the table from left to right, comparing every machine learning models to Jackal. So if we start with the linear regression, we see that for the recall, it is the model achieving the highest improvement with a near 13%, but it's still below the Jackal recall. The logistic regression achieved the highest precision against, but with not a high improvement. For accuracy, we see a big improvement too, but it is better, but we still obtain lowest recall. For the random forest, we see here that the recall improvement is not that much. It's a 7% improvement, a near 8% improvement, but it's still overall only 2% higher than the Jackal. So that did not give much more improvement. But for the multi-layer perception, we see here that we obtain 10% higher recall of near 91%. A decent precision at around 3% below the highest precision seen in the table with the logistic regression. And we also see that the multi-layer perception obtains the best accuracy at around 12% higher than Jackal. So overall, the MP model obtains the best result, and we also see that the recall is near the max possible value. It was not explained in the presentation, but we use an indexing technique to pre-select the interesting comparison. So because the Régie d'entreprise du Québec is consisting of 3.5 million enterprise, we cannot compare everyone between everyone, because it will resulting in really high amount of comparison around that will request around 45 or 42 days, complete days to compare all the data set just for one model. So we choose to use on indexing to pre-fill those comparison, and the maximum possible value that of recall that we can achieve using that technique is 93, is near 93. So we are pretty close to hit with a 91% with the perceptron multi-layer perception of with a value of n equal 10. So using a top-n approach greatly improved the result, and we achieved the almost maximum possible value for the recall. Now, about inference times. Since we want to use those solutions directly in the process of accessing a risk, we need to be to interest in the time consumption of a one model. We see first that our previously leading approach was Jacquard with a 0.25 second per business. So it's normal to see higher value here since we need to construct the similarity vector, information vector, sorry, consisting of various similarity algorithms. But we can see that our leading approach, the multi-layer perception, it's about a second longer. So considering that the process is done with speaking with the client, it's okay to take one longer second, and it's still really close to the Jacquard option. And we see that difference between the three algorithms are kind of close. The longest being the random forest, since we use 498 estimators, and the logistic regression taking the less time, but with minimal difference between the leading approach of material perception. So a summary of the machine learning algorithms. The use of name and address simultaneously with a machine learning algorithm improve the results. Using a top-n approach help achieve better results when n is greater than 1. And inference times of machine learning models are similar to using only a similarity algorithm. In conclusion, we have shown that using a similarity algorithm can achieve good results, but using a machine learning algorithm such as multi-layer perceptron can achieve greater results. And using a top and most similar approach where n is greater than 1 can improve the result, achieving almost the max recall value that we can have in our situation. And now for future works. Easy solution will be to try now to use word embedding to obtain better representation of the comparison between two entities. When we construct the similarity vector, we mostly rely on similarity algorithms. So now we could improve that vector with using word embedding, so the linear representation between words, to try to improve that information. One could also use a Siamese network consisting of two networks trying to compare the feature map, so the information vector between one entity and another one, to compare the difference between them and compute a symmetry after that. One could also use a spatial data to improve the address information and remove of more specific stop word using a TF-EDF approach for the stop word list. That could help in our case, since some words are really present, such as associé, construction, that don't give maybe enough information that we could remove to improve the information and remove noise in the names. I would like to acknowledge that research was supported by the Natural Science and Engineering Research Council of Canada and a Canadian insurance company, and my supervisor, Luc Lamontagne, for his mentorship. And now the reference. And if you have any question, I will be available to respond to any question that you have. Thank you to listen to my presentation.
Thank you, David. I don't know if there are any questions on David's presentation. I know that Pierre Gravel in the chat said that what will be the similarity between Université Laval in French and Laval University in English? Do you take into account the language of the address writing?
I don't take into account the language of the address, the name, sorry. So in that case, since we remove the accent, Laval will be a matched one from Jacquard. Like, let's say we have Jacquard, here it will be 1/3. In other case, will be different, but I don't take into account the language.
Okay.
Since most of the name are in French in the dataset, since we work in the Quebec, but if we want to do for all the Canada, that will be an interesting approach to improve the result too.
Also, I know there are, and in fact, I saw something like this not so long ago. There are some commercial products to standardize the address when you enter this, like example, in a web form and all this. So have you looked at this? Because I know that they may not be based on machine learning or NLP, general NLP. They are really specialized into normalizing the addresses. So how about this? I mean, does it compare? Have you made any kind of study on that?
I've explored some of the commercial possibilities. The major problem with that is, for myself, is the cost of the license. And the other one is when normalizing an address, mostly is we use the an external source such as Google API Maps. And the problem is it is costs a lot of money too. So we try to minimize the dependency of external source as much as possible, only using another data source. But that could be an interesting approach. And mostly the use of spatial data could help improve to and normalize the addresses. So all that could be consisting of maybe using the latitude and longitude, and you normalize the writing of the name. But we try our component address try to show that, and I think it's really shown that well, that without being without processing the address, it is really difficult to find similarities. But with a minimal one that just only remove the order of the address, we can greatly improve the result. So one can improve, maybe obtain greater result using special data or normalize a little bit more the addresses too.
In fact, I would even add that not everything is equal in there. I mean, if you look at the postal code, which is kind of relatively standardized, it is easy to get this into a regular form. This is, I would say, relatively reliable for matching companies in the same neighborhood. And how about not, because it's I would say much more standard, much more simple. So why not just maybe starting with matching the postal code to get, I would say, a set of possible companies?
It is a solution that I thought. The problem being that it's more of an indexing step than a comparison step.
Yeah.
So when selecting which entities that we want to compare, I use an approach based on an index, based on the name. So we kind of do something like that, where we conduct a list of all the possible match based on the name or the addresses. And the postal code was used in that, but I've tried to before, but it was shown to be really restrictive, because the data set that we have, the private data set, the postal code was generated, the address was generated using a preprocessing step that in some case the postal code is not always right, or the sectioning of the postal code have changed between times. So in some case, it was given poor result than using only the address component.
Okay, well, I see. And that's maybe lead I know there is a question from Alexandre Lepage, but I will just finish with one last comment. But I mean, somehow, if I understand well, you compare pair by pair, but you restrict maybe the corpus of pairs in which you will use for matching one given component. But you know, this is prone to false alarm, false positive, because if you have like 1,000 different address to match, or maybe 10,000, the issue here is that even though you have a really small rate of misidentification, you have like 10,000 times the chance of making a bad match, and that's may induce some error. So why not, instead of making pairwise comparison, making some more things like hashing the address, or maybe having something that is more restrictive, that will result in like maybe a set of 25 candidates in which you could be reliably make a verification pairwise.
I've tried also this approach using an hashing. The major problem is uh, names are sometimes really short, so it's difficult showing an interesting hash, resulting in instead of having let's say 25, it will be resulting in having like 20,000. So especially when removing the stop word, like let's say I have a name that is I forgot. I think it was 7 ink, and when removing the stop word, no, maybe not that one, but I remember that there was one name that if we remove the stop word, it will be only resulting in ink, and since inks appear in a lot of names, that name was matched with almost everything. So it was really difficult to hash the names since some are really short, and we choose to for mostly for time and finishing the work to only use an indexing which is only based on query. So let's say I wanted to find the name Beauchemin Inc. I will contact a query based on Beauchemin, and Inc. appears in at most in the name of the IRQ documents. But I've tried to, but it was really difficult. And maybe using spatial data, we could achieve that, because I know that in commercial database, address are used to index the entity. So that would be an interesting approach for using the spatial data too, and boosting the indexing.
Okay, I see. So maybe quickly, because it is about 4, so we'll need to quit quickly, but we have 2 questions on the chat. So there is Alexandre Lepage who said you don't take into account misspelling, so there is no spell correction done in your data?
The symmetry algorithms, you mostly rely on that. I did not show that one, but Liebenstein distance is based on the misspelling. So they is trying to find the minimal number of transformation to be done to one sentence, to one string to obtain the second one. So it's kind of take into action to consideration the misspelling, but we did not focus on trying to use specific one for the sonority. Sorry. So let's say it's called the double metaphone, which use a keyboard mapping. So let's say someone plays a S instead of an A, since they are near to each other. We try the both one name to find the symmetry between the two, but we mostly rely on the symmetry algorithm to define the misspelling consolidation, to take into consideration the misspelling.
Okay.
And for the second question, should postal code be given a larger statistic weight, given that it is often the most relevant information on a GPS search? Definitely. I've tried to improve that step instead of using only like a weighted mean. I explained a little bit more in my thesis too. I have a chapter, a section about that. It is impossible for some addresses to get over, from memory, I think it's 0.8, because orientation is most of the time empty and unit 2, so it gives a 0 automatically to the similarity, even if we compare the exact same address. And using the mean is difficult to obtain greater than 0.8 similarity. But I did not have enough time to improve that step, so we choose to only use mean average. But one could try to use like lesser logic segregation to find those weight, to allow weights on non-uniform weights between the component to compute the similarity too.
Okay, I see. So I think this is it. We have done a full hour. So thank you, David, for your presentation. And this is the last one for this summer. We will come back in September. So stay tuned. Stay tuned for who will present and when, because we may move another moment in the week. So thank you, everyone, and have a nice summer.
Thanks, Christian. Thanks, David. Bye-bye.